A roller coaster reaches the top of the steepest hill with a speed 1.4 meter per second. It then descends the hill, which is at an average angle of 45 degrees and is 45 meters long. What will its speed be when it reaches the bottom? Assume that coefficient of kinetic friction is 0.12. So what we have? This is a typical combination of kinematical and dynamical problems, two problems in one, packed in one particular problem. So we have separately solved dynamical piece and kinematical piece. Look, we are given velocity, we are given length. They never comes up in dynamical problems. This is entirely kinematical information. But at the same time we have angle and we have coefficient of kinetic friction. They are given to us to solve dynamical problems. So first of all, we will solve dynamical problems. We will find with what acceleration the roller coaster will move downward over the hill. So let's assume that this is roller coaster. I will use this as the box, but it doesn't matter. To find acceleration, again, you have to start drawing free body diagram. You will have force mg directed downward, force with which Earth attracts our roller coaster. You will have normal force, which is perpendicular to the surface over which a roller coaster moves. And you have kinetic friction force, which is opposite to direction of motion. Now we have here angle theta. This is our 45 degrees. As usual, you have to write second Newton's law. Second Newton's law gives us a relationship which connects acceleration of the roller coaster with the net force acting on the roller coaster. Net force is sum of all forces acting on our roller coaster. In our case, three forces we have. So this is N plus mg plus fk. And this is the only equation which we have for the dynamical case. Now, to be able to solve this vector equation, we have to split it onto the horizontal and vertical components. So what I will do, I will introduce coordinate systems. X-axis will be parallel to the surface of the hill, and y-axis will be perpendicular to the surface of the hill. You see that N is vertical, Fk is horizontal, but mg is neither one. So as usual, you have to split mg onto horizontal and vertical component. So this is 90 degrees angle. If you look at the triangle, this one, and this angle theta, you see that angle theta is here. I explained in detail why it happens in the previous problem. So if you look at the right triangle, you see that this is leg adjacent to the angle, so it's equal mg times cosine theta. This leg is opposite to the angle mg times sine theta. As soon as you split your non-vertical, non-horizontal vector onto the vertical, horizontal components, you can forget about this vector because these two rows plays exactly the same role as mg. Now we have four arrows in our case, and all of them either vertical or horizontal. Clearly, acceleration has direction along the hill. It's horizontal. So we can write our equation, basically rewrite vector equation for the horizontal and vertical axis. We have A, which is positive because it's horizontal and coincides with the direction with the x-axis. Then we have this horizontal component of mg force, mg times sine theta, and we have minus fk because it's opposite to the direction of motion. It's not a vector, it's just the value of the kinetic friction force. Then we have y-axis. We do not have any vertical acceleration, so it's 0. 0 times mass gives you 0. Then we have positive n and negative component of mg force, minus mg cosine theta. As soon as you deal with the friction, you have to add the connectionship which exists between friction force and normal force. Fk is equal mu k times n. Our goal is to find acceleration, so we'll start from the first equation, ma equal mg sine theta, and put here fk. So minus mu k times n. And you can find from the second equation, n would be equal mg cosine theta. So you will be able to put here your n. You have mg sine theta minus mu k mg cosine theta. So we have this equation. Now you see that m comes up in all terms from the left from the right. You can cancel this, and you will have your acceleration, which will be equal g. I will factor this. Sine theta minus mu k cosine theta. This is our acceleration. It's not a big deal to solve this equation and find numerical value for this acceleration. I will not do that. Then, after you solve this dynamical part of the problem, you have to solve kinematical part of the problem. We have motion over the straight line. This is our initial point. This is our final point at the bottom. So I will represent this as straight line piece. I will put axis, x in the same direction as I used for the dynamical case. Now I know that initial speed here, v initial, equal 1.4 meter per second. I need to find final speed, v final, at the final point. This is my goal. And I know that I have acceleration a, which points from initial to final point. What additional I know? That the distance between initial and final point is 45 meters. So if I put origin at initial point, x initial would be equal to 0, x final will be equal 45 meters. Now, you see that we have x initial, x final, v initial, and acceleration. We are looking for the v final. Kinematical equation, which connects all of these components, is x final equal x initial plus v final square minus v initial square divided by 2a. So from this equation you can find your v final. V final would be equal square root of v initial square plus 2a x final minus x initial. Do not forget to calculate a and plug in this equation, and you will be able to solve the problem completely.